and the PDFs online. So if all goes according to plan, all right up there, it'll put it on the PDF. You'll be able to watch this on the video. We'll see. Okay, did everybody see the homework assignment and do it? That's another key part. Okay, good. Perfect. So today I'm going to just be doing mathematical preliminaries for this class. There's a couple of key ones that are going to come up over and over again. And then on Friday we're going to do the first quiz, which is just going to be based on these two daily assignments from Monday and Tuesday. And then I'll probably play that violin a little later. I don't know whose that is, or small guitar, or whatever. It doesn't matter. Just strum it really hard. Okay. So the mathematical preliminaries that we're going to get into today are ordinary differential equations, and let me and the way that we're going to solve differential equations in this class, you only have to worry about one technique, separation of variables. And then we're going to do three other things that you're very used to, but you might not be used to doing with vectors. Largely they're the same, but I just want to be clear about those. So derivatives of vectors, product rule with vectors, and chain rule. And this one, number 2, we're going to get into cases later where we have a coordinate system that's changing orientations. I mentioned last time that there's two ways that a coordinate system can be non-inertial. The origin can be accelerating, or the axes can be changing orientation. So we're going to be, what I'm going to do right now is how to do derivatives of vectors with a non-rotating coordinate system. Okay. Like what you're used to. Okay, so we're going to start with ordinary differential equations. Okay, so here's the approach that we're going to follow when you see a differential equation. And I'm going to make you be pretty explicit about it at first. Later on, you can leave. You don't have to write these steps or whatever, but I just want you to get into a good habit about how to think about a differential equation when you see it. Because I think up to this point, like, mostly you've seen differential equations in differential equations class or whatever, and so you're working on a specific topic or whatever. When you see one in the wild, it's a little bit scarier. You just look at this thing and you're like, oh my God, like, I've learned a million things. Do any of them apply? So this is sort of a systematic way to think about it. Before you can start trying to solve it, you have to know 4 things. The first one is it an ordinary differential equation or a partial differential equation? Which one is good and which one is bad? Yeah, ordinary is much, much better than partial, from your perspective, as the person who has to solve it. So an ODE, well, what's the difference? What's the difference between those two? Anyone remember? Well, one thing is, like one giveaway is, are there partial derivatives or total derivatives? But the definition is it's an ODE if it only has one independent variable. Okay? And if that's the case, all the derivatives you see are total derivatives. They're D's, not squiggly D's. Partial differential equation has, more than one independent variable. So what you see are partial derivatives. For example, an equation that depends on x and y independently. Your independent variables are the location in a plane, and the function is the height above the plane or whatever. A differential equation where that's the function is going to be a partial differential equation, two independent variables. The second thing related to that, I guess, is identify the independent variables and the dependent variables. Do you think it's dependent or ent? I think ENT, yeah. That sounds right to me. Dependent variables. All this stuff still applies even if I spell that wrong. Okay, so the independent variables are the arguments of the function. The dependent variables, these are a function. Okay, so let me write this. These are, this is a function argument. The dependent variables are functions of the independent variable. And if you're solving a differential equation, this is what you're trying to find. Okay? Okay, so you can have a ordinary differential equation, the good kind, the kind that we're going to be able to approach in this class, with one independent variable. It needs that to be defined as an ordinary differential equation. But it could have 100 dependent variables. Okay, as long as you have 100 differential equations to solve for those 100 functions. Okay, that's still an ordinary differential equation. So you could have a system of differential equations where you're trying to find x of t, y of t, z of t. That's 3 dependent variables, but it's a system of ordinary differential equations because you only have one independent variable. Okay. Third, you need to identify the order of the differential equation. And the order is the highest derivative that you see. So if you so if you have a differential equation with a second order derivative, then that's a second order. With a second derivative, then you have a second order differential equation. And then the last thing related to C is how many boundary conditions are required to solve this, and do we have them? That's sort of two questions, but. So here are the examples that I'm going to, and let me sort of show. So these two are sort of grouped together. These two are sort of related, grouped together. All my PDFs are going to have all these little freckles all over them because I'm left-handed and my hand touches the stupid screen. Can't help it. Okay, so here are the examples. So the first one, dx dt is equal to 5tx plus t squared. The second one, 2 dz dx plus 3 dz dy is equal to 10xy. And the third one, x dot y dot as a vector is equal to the matrix 10, 0, 0, negative 5 times xy as a vector plus 10 cosine 3t negative sine t. Okay, so we're going to go through these steps with these three examples. So the first one, we have dx dt. I don't know why I'm writing these twice, but dx dt is equal to 5tx plus t squared. So let's just go through those four things to identify this differential equation so we're ready to get started. First, is this an ordinary or a partial differential equation? That's ordinary. How do you know? Just remind yourself. This is the part where you just beat this stuff into your head. One independent variable, and that's reflected in the fact that the only derivative is a total derivative, not a partial derivative. So it's ODE. And so internally, you don't write this on the paper, but internally you say, yay. Actually, in a sense, another way of thinking about it is when you see an ordinary differential equation, you're sort of like, oh no, like my professor might want me to solve this. If it goes to a partial differential equation, then you're like, he doesn't want me to solve it. Like, that's not even part of the problem. He just wants me to set it up or whatever. But these, in some cases, they'll want you to know how to solve. Okay, what are the... Well, it's ordinary, so we know there's only one independent variable. What is it? X is the dependent variable. X is a function of time. How can you tell that from the... Yeah, it's the independent variable is the one you're taking the derivative with respect to. Okay, so the independent variable is t, and in dynamics, most of the time, maybe all the time, I can't think of any counterexamples right now, t is going to be the independent variable. So t will almost always be the independent variable. What about the dependent variable, or this is ordinary, which means we have one independent variable, but we can have any number of dependent variables. So what is or are the dependent variable? X. So we're looking for a function x of t. That's what we want to solve. Okay? There's nothing else in there, so that's it. That's what you're always trying to do. Third, what's the order of this? There's a first order derivative, so we don't care about this. That could be to the millionth power times cosine of t to the millionth power. All we care about is the order of the highest derivative. So first order, because it's a first derivative. What am I doing? Ordinary. Okay, it's an ODE. Oh, that should have been C, right? And then the last one, how many boundary conditions do we need? Okay, so here's how you know how many boundary conditions you need. Well, you can think of, I mean, it's not as, solving differential equations isn't always as simple as just integrating, but you can think of your, in essence, integrating for every derivative you have. So if you have a fifth order differential equation, you're going to have 5 constants of integration, and those, you're going to need boundary conditions to solve for each one of those. Okay? If you have a system of ordinary differential equations, say you have a system of 2 second-order differential equations, okay, then you're solving for 2 dependent variables, 2 functions. Each of those functions you're solving for is going to have 2 constants of integration. So you'll have 2 times 2, 4 boundary conditions. So in this case, you have one equation with one constant of integration so you need one boundary condition. And that'll be in the form of like when time is equal to 0, x is equal to 5. Okay? It'll give you something to match those up. do we have it in this case? No, I didn't give anything like that. So, any questions about that one? These little things are going to drive me crazy, but it's going to be funny for you to watch me dissolve into madness slowly. Okay, so the second one. The equation was 2 dz dx plus 3 dz dy is equal to 10 xy. Okay, is this ordinary or partial? Partial. Because it's you see partial derivatives. I mean, that's the simplest way to recognize it. There are two independent variables because you have a partial with respect to x and a partial with respect to y. And so okay, so that's a partial differential equation. That's not good, except that it means that no one expects you to solve it. What are the independent variables in this case? It's partial, so we know that there are more than one. X and y. And how do you know it's x and y and not z? That's right. It's what you're taking the derivatives with respect to. Those are the independent variables. Whoops. The dependent variable. Now, with a partial, you could also have more than one dependent variable. The number of dependent variables doesn't have any effect on the kind of differential equation it is. What is or are the dependent variables? Yep. So in this case, you'd be looking for a function z and what of x and y. Yep, very good. And that's what you'd be trying to solve for. So solving this differential equation means finding that function z of x and y. And then the last one, the question, oh no, there's two more. What's the order of this partial derivative, partial differential equation? It's first order. So this would be called the first order PDE, and there are certain approaches for solving first order PDEs that are different than approaches for second order PDEs and so on. And then the boundary conditions, well, with PDEs, that gets more complicated. So we're just not even going to go into that right now. We know we're not going to try to solve those anyways, but the short story is that to solve a PDE, you need functions as your boundary conditions as opposed to values for your boundary conditions. Okay, you need whole continuous functions. Any questions about that one? Okay, and then the third example, x dot, y dot is equal to the matrix 10, 0, 0, negative 5, times xy plus 10 cosine of 3t negative sine of t. How many people have seen matrix multiplication like this before? Or how many people have not? It's easy to do. Okay. Well, so I'm going to rewrite this as two separate equations. This is just one, there are two different ways to write this. So this is a system of equations. The first one says x dot is equal to 10x plus 0y plus 10 times cosine of 3t. And the second equation says y dot is equal to 0x minus 5y minus sine of t. Okay, so first of all, this is the first one that we've looked at that's a system of equations. Is this system of equations, is this a system of ordinary or partial differential equations? Ordinary? Yes. That's right. If you talk quiet enough, I'll just assume that you said the right thing. So that's a good strategy. Okay. So this is a system of ordinary differential equations. Yay! That means that we know that there is we know that there's only one independent variable. And what's that in this case? Oh, okay. Yeah. I think I might have mentioned this notation last time, but we're going to use this notation a lot anyways. So let me write that down first. So independent variable is t. Okay, so x dot means dx dt, y dot means dy dt. Maybe you see the pattern. You can do that with any variable. So that dot means a total derivative with respect to time. Okay? Okay, that's enough. So it means a total derivative with respect to time. So our independent variable then, if this one says dx dt is equal to all this stuff, this one says dy dt is equal to all this stuff, all the derivatives are with respect to time, so the independent variable is time. What about the dependent variable or variables? Yep, so we're looking for the functions x of t and y of t. We want to solve for those two. What about the order? Yep, so this is a system of two first order ODEs. That's how you would describe that. And so based on that, what do we need for boundary conditions? That's right. We need one for each first order differential equation. So we need two boundary conditions. Okay. So now the second question is, well, the ones that are ODEs we might be able to solve. So the question is, what techniques? And I know a lot of you are taking differential equations at the same time you're teaching this, so you haven't gone into too much yet. But the one technique we're going to use is probably the first one they teach in differential equations. That should be a question mark. So in this class, there's only one you have to worry about. And that one's called separation of variables. And not only is that the only one that we're going to deal with in this class, I think it's safe to say that through the rest of your time in engineering classes, and even largely your grad classes if you take graduate classes or whatever, if you derive an ordinary differential equation in any of your mechanics classes, the only technique that your instructors will expect you to be able to carry out is separation of variables. Anything else, they'll give you hints on it or whatever. They'll tell you what to do. They'll give you the background. Because they don't expect you to remember all the things that you learned how to do in differential equations. But they will expect you to apply separation of variables without any prompting or whatever. So that's what we're going to focus on, okay? Okay, so here's separation of variables. I'm going to abbreviate that SOV. So if you're given an ordinary differential equation that can be expressed this one way, okay, so if you're given an ODE that can be expressed as dy dt is equal to f of y times g of t. Okay, so first let's think about, so we see this thing. So first, is that ordinary or partial? And how do you know? That's ordinary because we have a total derivative and only a derivative with respect to time, so that's an ODE. Also, I said up here above that it's an ODE, so that's another way you can tell sometimes. So there's one independent variable. What's that? T, the derivatives with respect to t. How many dependent variables are there? Yeah, in this case, the idea is that f of y and g of y are known, and we're trying to find, we're just trying to find this function y of t. You can tell because we're taking the derivative of y with respect to t. Okay, it's a, what's the order of this differential equation? First order. And then the boundary conditions, let's forget about that for now. Okay, so the way to solve this is you're going to rewrite it by moving all the t stuff over to the right and all the y stuff over to the left. So we have dy over f of y is equal to g of t dt. And then you can integrate both sides. Over here you have the integral of dy over f of y. Over here you have the integral of g of t dt. You have one constant of integration. I mean, you have one constant for each of these, and they're lumped together into a single constant. And you're going to use the boundary condition to solve for the constant of integration. Okay. Any questions about that idea? So let me go through how many examples? 2 examples. Okay, so let's say first we have the differential equation. Y dot is equal to yt squared, where y of 0 is equal to 10. Okay, so let's go through these, find these 4 things that define this differential equation. First, is it ordinary or partial? Yep. What's the independent variable? T. What's the dependent variable? Yep, we're looking for the function y of t. What order is it? And then last, how many boundary conditions do we need? Yep, it's a single first order differential equation, so we're going to have one constant of integration. So we need one boundary condition. Does it look like we have it? It's possible for boundary conditions to be in the wrong format for you to use, but we do have one boundary condition. It looks like this will work. So we have one, and that's a good sign. Okay. Okay, so I'm going to rewrite this equation as dy dt is equal to yt squared. Wait. That wasn't the one I wanted to do. Oh, yeah, it was. Oh, that one's so... Okay. Okay, let's do it. All right, so separate, get all the y stuff over here with the dy, all the t stuff, get dt over with all the t stuff. So we have dy over y is equal to t squared dt. And now we'll integrate both sides, and we get natural log of the absolute value of y is equal to integral of t squared is t cubed over 3. Each of these two integrals has a constant. You could call them like C1 and C2, right? They're arbitrary. So you can add them both together and lump it into one arbitrary constant of integration called C. Now we have to solve this thing. So what if, let's do it first just thinking of positive y. Okay, then we have natural log of y is equal to t cubed over 3 plus c. Anyone remember how to solve that? Take e to the power of both sides. So you got e to the natural log of y is equal to e to the power of t cubed over 3 plus c. What's e to the natural log of y? Y. This thing, so, is e to the t cubed over 3 times e to the c. Okay, so I'm going to rewrite that as c1 e to the t cubed over 3. That e to the c I'm just calling a new constant, c1. Okay, so there's the function. The function has that form, but we don't know what that c1 is, and that's where we use the boundary condition. So what? So that's right. So what we're given is that when t is equal to 0, y is equal to 10. So we're going to use the boundary condition to find C1. So at t equals 0, y is equal to 10. That says 10 is equal to is equal to C1 times e to the 0. Okay, I'm just plugging in for that t value. And so 10 is equal to C1 and therefore the function that we want, y of t, is equal to 10 e to the t cubed over 3. Any questions about that? All right. The next example in dynamics and physics, you have a lot of second-order differential equations because acceleration is a second derivative of position. So let's say that we have, okay, so here's an example of a second-order ODE. So x double dot is equal to 2t squared, where x of 0 is equal to 2, and x prime of 2 is equal to 4. Okay, so this idea of separation of variables only works for first-order differential equations, but x double dot is the first derivative of x dot. So we'll just do it in steps, and first we'll do it with our dependent variable being x dot, and then we'll do it with our dependent variable being x. Okay. So this is an ordinary differential equation. The independent variable is t. The dependent variable is x of t. Second order. And so we need two boundary conditions. Again, there's no automatic guarantee that the two boundary conditions you have are of the right form, but it's a good sign anyways that we have two of them, so we'll try to use them. All right, so the first step is I'm going to write this as d dt of x dot, and that's equal to 2t squared. Now I'm going to use separation of variables, and you get dx dot is equal to 2t squared dt. We can integrate that. The idea here is this x dot is our variable. We could have called that something else z and gone through it that way. But if you take the integral of dx dot, you get x dot. Take the integral of this stuff and you get 2t cubed over 3 plus a constant of integration. I'll call it C1. If you look at the boundary conditions now, you might be able to see that we can actually use that second boundary condition to find C1 right now, but let's just go to the end and then see what we have. That's what I'm used to doing. So now we'll rewrite this as dx dt is equal to 2t cubed over 3 plus C1. And so dx is equal to 2t cubed over 3 plus C1 dt. Integrate both sides, and you get x is equal to t to the 4th over 6 plus C1t plus C2. Now we can use our boundary conditions. The first one says when time is equal to 0, x is equal to 2. So 2 is equal to 0 plus C2. So C2 has to be equal to 2. And then the second boundary condition says when t is equal to 2, x dot is equal to 4. So using this equation, we have 4 is equal to 2 times 2 cubed over 3 plus C1. Solve for C1 and you get negative 1.333. And so x of t, if you plug both of those back in, is equal to t cubed, no, sorry, t to the 4th over 6 minus 1.333 t plus 2. Okay? Any questions about that? Yes?
Is it right if we leave it in the exact form? Like when I wrote it down as negative 4/3.
Oh, yeah, sure. Yeah, that's fine. Any other questions? Okay, I'll post the assignment for today, later today. And so remember, the first thing we're going to do on Friday is that first assignment quiz. It's going to be based on the quiz from Monday and the quiz from today. Okay. Based on the assignment from Monday and the assignment from today. Yes.